In the last lecture, we did several examples on applying first law of thermodynamics for a closed system while reading property values from tables. Today, we are going to continue with the same topic, but I'm going to talk about incompressible substance, ideal gases, polytropic process, and then application of first law when we have ideal gases. Now, before we do that, I want to clarify a few things we discussed in the last class. We discussed, for example, if say temperature and volume are given, okay, for a pure substance, then how to determine the state, whether it is subcooled liquid or it is superheated vapor. We talked about that. Now, one addition to that is, let us say what is given is temperature and internal energy, or say pressure and internal energy. Then how to determine based on this information what is the state? If U is greater than Ug, that means energy is higher than the energy of saturated vapor at the given temperature or at the given pressure, then it will be superheated vapor. So it's very easy to remember because high energy means it will be superheated vapor. If U is less than UF, that's low energy, energy is less than the energy of saturated liquid, then it will be subcooled liquid. Okay. And same is true if we have, say, temperature and enthalpy are given, or pressure and enthalpy are given. So in these cases also, we can compare H with HF and Hg. If H is greater than Hg, it will be superheated vapor. And if it is less than HF, it is subcooled liquid. And between HF and Hg, it will be two-phase. Okay, so that is an addition to what we discussed in the last class. Now, along with that, sometimes we may have a situation. Let me give you an example. Let us say it is given that pressure is 25 megapascal and temperature is let us say 400 degrees C, and we have to determine the state. Okay, now if you try to find, okay, let me look at saturation temperature at given pressure at 25 megapascal. Actually, you won't find this value in the table because 25 megapascal is above the critical pressure for water. So this pressure is not even there in the saturated liquid vapor table because there is no distinct phase change at this pressure. This is supercritical pressure. Okay, this pressure actually is greater than critical pressure. So you can't read saturation temperature from table. Okay, so the convention is, let me first draw a diagram. Let's say we take temperature volume diagram. This is vapor dome, and the constant pressure curves on this diagram, you know, those are like this. So this is for a pressure that is less than critical pressure. This is the critical point, and if pressure equals critical pressure, then curve will be like this. There will be an inflection point here, and if pressure is above critical pressure, it will go like this. It will be above this. So you see, there is no distinct phase change process for this. So but you can say that here it is liquid and here it is vapor, superheated vapor. Okay. But the convention is, if temperature, this corresponds to critical temperature. So if the situation is such that if pressure is greater than critical pressure, okay, then the convention is, if temperature is less than critical temperature, that means it is in this region. it is called subcooled liquid. And if temperature is above critical temperature, that means above this point, above this line, then it is superheated vapor. So that is another addition. So this will be the situation if you are given pressure that is actually supercritical pressure. So there is no data for saturation temperature in the table, but still this understanding we can use. Okay, so today first I am going to talk about what is specific heat. Specific heat is a property that characterizes thermal energy storage capability of substances. So different substances have different thermal energy storage capabilities, and how to characterize them, that is characterized by what is called specific heat. Let me give you an example. Let us say we have, this is 1 kilogram of iron, and we have 1 kilogram of water. Both are at atmospheric pressure, and say both are at 20 degrees C, and we want to change their temperature from 20 to 30 degrees C. So we want to heat them. Okay, so they are different substances, but we want to heat them by same amount. It turns out that for iron, the amount of thermal energy we'll have to supply is 4.5 kilojoule to take it from 20 to 30 degrees C. And for water, it is around 42 kilojoule. So you see, we are heating same amount of substance, 1 kilogram, by same temperature rise, 20 to 30 degrees C, but iron requires only 4.5 kilojoule, whereas water requires almost 10 times of that, 42 kilojoule. So which substance has more thermal energy storage capability? Water has higher thermal energy storage capability. Okay. So in order to characterize this, we have a property that is called specific heat. Now, how this specific heat is defined? It is defined as energy required to raise temperature of unit mass of a substance. So you can say 1 kilogram, 1 gram, or 1 mole, 1 kilomole, but it is per unit mass. Energy required to raise temperature of unit mass of a substance by 1 degree. Okay, that is specific heat. But actually this definition is not complete, because if you want to heat a substance, okay, by 1 degree, 1 kilogram of that substance, because heat addition, heat transfer, it depends on the path. So although we are increasing temperature by 1 degree, the amount of energy required to raise that will depend on the path. Okay, so this definition is actually not complete. So I have written here, it depends on the process. Okay, and here is an example. If we take 1 kilogram of helium, okay, and we want to increase its temperature by 1 degree C. So its temperature, let us say its temperature is 25 degrees C, we want to increase it to 26. And we can do the process in different ways. So one possibility is if we are doing it at constant volume. Okay, it turns out that amount of heat transfer required is 3.12 kilojoule. Another possibility is if we are doing it at constant pressure. For this case, amount of heat transfer required is 5.19 kilojoule. Okay, so you see, in both cases, we are increasing the temperature of 1 kilogram of a substance by 1 degree C, but the amount of energy required, amount of heat transfer required, depends on the process. For constant pressure process, it is greater than constant volume process. And the reason is that in case of constant pressure process, this piston moves as there is heat addition. So this heat addition has to increase the energy of the gas and also do work on the surrounding, because this piston moves. Whereas in this case, all this energy is going into, all this heat transfer is going into increasing the energy of the gas. There is no work involved here. Okay. So now we define, so there are infinite possibilities actually of processes. This is constant volume, this is constant pressure, but there are infinite possibilities how you are increasing the temperature by 1 degree. But in thermodynamics, we are interested in two special cases. Those are the constant volume case and the constant pressure case. So I want to complete this definition now. So if we say energy required to raise temperature of unit mass of a substance by 1 degree when the process is executed at constant volume. So we are specifying the process. When the process is executed at constant volume, then it is called specific heat at constant volume. We write that as CV. This is specific heat at constant volume. Okay. And if the process is constant pressure process, we are doing the same thing, increasing temperature of unit mass by 1 degree, but at constant pressure. Then the specific heat is called specific heat at constant pressure. We indicate that as CP. So this is specific heat at constant pressure, and this is the number for helium as we considered here. Okay. So at this point, it may appear that Cp and Cv, because actually these are not properties, because properties are associated with the system, but it looks like these are amount of heat transfer for a constant volume process and amount of heat transfer for a constant pressure process. So actually it may appear that these are not properties, they are associated with the process. Okay, so I'm going to clarify that, and I'll also show that we get this equation for CV. CV is del U del T at constant volume. So change in internal energy with change in temperature at constant volume. CV is that. And CP is change in enthalpy with change in temperature at constant pressure. I'm going to derive this briefly. But after derivation, now I can argue that these are properties, because you see U is a property. U is a property of the system, and we are taking a derivative of U with respect to temperature at constant volume. So everything is a property here. So CV is also a property, and similarly CP is also a property. Okay. And we also define specific heat ratio. I have used symbol K for that. Some books use symbol gamma for that. So this is defined as ratio of Cp to Cv, and this is always going to be greater than 1. Okay, because Cp is greater than Cv. So let us derive these expressions. Okay, so first let us consider a constant volume process. Okay, so there is heat addition, and if we write first law for this, like generally you write change in internal energy is Q minus W. Okay. Or if it is a stationary system, there is no change in the kinetic energy and potential energy, then delta E is same as delta U. So delta U is Q minus W. So this is the equation in the integral form. We can also write as delta U equals Q minus W. Okay, so these are uppercase symbols and these are lowercase symbols. The difference is we divided this equation with mass of the system. Okay, so this change in internal energy becomes change in specific internal energy, and this Q is heat transfer per unit mass. This is work transfer per unit mass. So we have to be consistent. Either everything is lowercase or everything is uppercase. So this is the integral form of the equation. We can also write this in differential form, which will be like du equals delta Q minus delta W. Okay, this is the differential form. And now we are writing delta for Q and W, and reason for that is because these are path functions. They are inexact differentials, whereas U is exact differential, so we write U for that. Okay, so that is first law. And if we apply this law for a constant volume heat addition process, this work term will be 0. So you will get du equals delta Q. Okay, if it is constant volume process. And see how CV is defined. CV is defined as amount of heat transfer per unit mass. Okay, so this is heat transfer per unit mass because this is lowercase q. Per unit rise in temperature, so I can write that as say if temperature rise was delta T because of this heat addition over delta T, or say dt at constant volume. Okay, that is the definition of CV. Amount of heat required per unit mass, per unit rise in temperature at constant volume. But this dq at constant volume is actually du. So what you get is CV equals del u del T at constant volume. Okay. Okay, so CV is a property now. So you can write CV as a function of temperature and volume, or as a function of temperature and pressure. Okay, because if from state postulate, if you fix two properties, then other becomes fixed. So CV is a function of two variables like that. Or you can write it as a, yeah, write it in this way. Okay. Now instead of constant volume process, if the process is constant pressure, so now think of heating in a piston cylinder device. There is heat addition and it's constant pressure process. Okay. Then again, beginning from the first law, that is du equals delta Q minus delta W. In this case, there is work exchange because this piston is going to move when there is heat transfer at constant pressure. But we can combine these two terms, this boundary work term with du term, and that becomes dH. We talked about this previously also. So you get dH equals delta Q, okay, for constant pressure process, for constant pressure heat addition. Now see, what is definition of CP? CP is amount of heat transfer per unit mass, okay, per unit rise in temperature when the process is executed at constant pressure. Okay. So this becomes, because this heat transfer at constant pressure is same as change in enthalpy. So this becomes change in enthalpy or change in temperature at constant pressure. Okay, so that is CP. Okay, and this is also a property. So you can write like CP is a function of say pressure and temperature, or it is a function of say temperature and volume. Okay, so like that. So these are specific heats. Okay. Okay, now I will talk about incompressible model for solids and liquids. In engineering, in solving engineering problems, we use several models which are approximations, but which are very good, because we don't want exact answers. We want an estimate which is a good estimate. And solids and liquids, although they are not perfectly incompressible, but their compressibility is very small, so we can treat them as incompressible. Okay, let us see if we treat solids and liquids as incompressible, then what do we get? We get very simple results which are very easy to use, and as engineers we would like to use those results. Now incompressible substance means if its volume is constant, so it doesn't change. Okay, no matter you try to compress it or you try to heat it, its volume is not going to change, then it is incompressible. So solids and liquids are almost incompressible. It turns out that if volume of a substance is constant, it does not change, then internal energy is a function of temperature only. Okay. In general, you will write internal energy as a function of two variables, like a function of temperature and volume, or a function of, say, temperature and pressure. But for an incompressible substance for which volume is constant, we get U is a function of temperature only. And the derivation of this, the mathematical thing, actually, we'll see that later on. We need thermodynamic property relations to show this. Okay. Okay. Now, the definition of CV is del U del T at constant volume. But if U is a function of temperature only, when taking this derivative, we don't care about V because V is constant anyway. That is the nature of the substance. So you can write this as du dt. Instead of partial derivative, you can write total derivative, du dt. Okay. So now this means that because U is a function of temperature only, so CV also is a function of temperature only, because CV is du dt. So this thing is a function of temperature only. Okay, we get that. We are talking about incompressible substance here. So that is CV. Okay. Now look at enthalpy. Enthalpy by definition is U plus PV. Now the definition of CP is del H del T at constant pressure. Okay. So if we differentiate this with respect to temperature at constant pressure, you see V is constant, incompressible substance, and we are keeping P also constant. So this term is constant, its derivative will be 0. Okay. So del H del T at constant pressure will just become du dt, and it will be total derivative because U does not even depend on pressure. So it is du dt. So what do we get? It means that Cp, you see Cp is du dt and Cv is also du dt. So we got Cp equals Cv for an incompressible substance. So we don't have to say Cp and Cv, we just say C. There is only one specific heat, and it is a function of temperature. It is not a function of two variables, it is a function of just temperature. Okay, so that is the result we get for an incompressible substance. So this you must remember. For an incompressible substance, there is only one specific heat, and we just call that C. We don't have to say Cp or Cv, and it is a function of temperature only. Okay. Now we got C is du dt, okay, or du is C dt. If we integrate this, du becomes delta U, and we can take the value of C at some average temperature. Okay, actually C is a function of temperature, so when you integrate this, C is inside the integral, but its variation is not very high, so we can take it outside at some average temperature. So delta U becomes C average times delta T. So we can use this expression for change in internal energy for an incompressible substance. So it's very easy to use. We just need value of C, and in the appendixes of various books, the value of C for various solids and liquids are given. Okay, so we can use this expression. And let us look at change in enthalpy now. H by definition is U plus PV. If I differentiate this, you get dH equals du plus, because V is a constant, we get V dP. Okay. And we integrate this expression, you get delta H equals delta U plus V is a constant, V delta P. So we can use this expression for change in enthalpy of an incompressible substance. It will be change in U, which will be C average delta T, or you just say C delta T. If the value of C is given, it will be just C delta T plus this term, V delta P. And this, the effect of this V delta P term, it is negligible for solids. For solids, we just neglect this term. Okay, for liquids, we may have to consider this. For liquids, there are various possibilities. Let me indicate those. Okay, we have delta H is delta U plus V delta P for an incompressible substance. For liquids, one possibility is, for example, say liquid is flowing through a pipe. and we want to determine what is change in enthalpy across the pipe, okay, as it flows. And if we neglect change in pressure, delta P is 0, there will be some drop in pressure. If that is negligible, that is 0, you get delta H is same as delta U. Okay, so you have to just remember this expression. This one is a special case of that, when pressure is constant. Okay, or other possibilities could be when, say, temperature is constant, and this happens when we pump a liquid. So liquid passes through a pump, and in pump there is negligible change in temperature. There is rise in pressure but negligible change in temperature. So because temperature remains constant, this delta U, that is C delta T, this term is 0. So delta H will be V delta P. So get delta H will be V delta P. Okay, so these are special cases of that. Okay, and let me also clarify one thing. So these equations are applicable only for an incompressible substance. So for example, let us say this is vapor dome, say PV diagram, and say the substance is water. Okay, it could be any substance, we are taking water, and say its initial state is here, 1, and say final state could be inside the vapor dome or could be here. Okay, I'm just taking, say this is the final state. Okay. And we have to determine delta U or delta H. Can we apply the equations we derived, C delta T or the equation for delta H? No, we can't do that, because at state 1 it is incompressible, but it goes to state 2, and at state 2 it is not incompressible. Okay, so you're not going to use the equation. These equations are to be applied when it is incompressible throughout. Okay, so we can't do that here. So in this situation, you will have, what you will have to do is you will take H1 as enthalpy of saturated liquid at same temperature. We talked about this previously. Okay, or U1 as internal energy of saturated liquid at that temperature. You'll use table to get that, and similarly for 2 you are going to use table and then get delta U and delta H. But if the situation is you have state 1 is here, and let us say this is state 3, so it's water but it is incompressible, it remains liquid, so then you can use the equations we derived for incompressible substance. Okay, for solids you can always use those equations, because solid we can treat as incompressible. Okay, so we are talking about these special cases now which simplify our life very much. So in general you have to read all these values from tables, but if we treat the substance as incompressible, you see the life becomes very easy. Delta U is C delta T and delta H is delta U plus V delta P. So these are simplifications. Another simplification is ideal gas. And before I talk about that, we'll talk about what is called generalized compressibility chart. And this analysis is applicable for gases. It is not for liquids and solids. We are talking about gases. So if we define a compressibility factor Z as PV over RT, okay, P is pressure, V is specific volume, R is gas constant, T is temperature. And in this equation, temperature has to be in Kelvin. Okay, it can't be in Celsius, it is in Kelvin. Or this is also equal to PV bar. So whenever I put a bar, it means it is per mole. Let me clarify that. See this V, this is specific volume. Its units are cubic meter per kilogram. Okay. This V bar This is also specific volume, but instead of per kilogram, it is per mole. So its units are cubic meter per mole, or could be cubic meter per kilomole. So it is on a molar basis. Okay. And similarly, we have in the equation you see here, there is R bar. This is universal gas constant. Okay. This universal gas constant is, its value is, sometimes we indicate that as R bar or as RU. That is universal gas constant, and its value is 8.314. This you must remember, joule per mole Kelvin. Okay, so those are the units because it is on a molar basis. Okay, joule per mole Kelvin, that is why we put a bar here. It is on a molar basis, or RU, universal gas constant. Or alternatively, you can write as 8.314. It will be kilojoule per kilomole Kelvin, same thing. Okay, now the gas constant R is gas constant. This is not universal gas constant. It is different. This is universal gas constant over molecular weight of the gas. M is molecular weight of the gas. Okay, for example, what will be gas constant for oxygen? It will be universal gas constant, that is 8.314 joule per mole Kelvin. Divide this with molecular weight of oxygen. Molecular weight of oxygen is 32. So it is 32 gram per mole, or you can write as 0.032 kilogram per mole. Okay, 0.032 kilogram per mole. So you see this mole and mole cancels. So the answer you will get will be in joule per kilogram Kelvin. Okay, this is joule per kilogram Kelvin. So see, the gas constant is on per kilogram basis, whereas universal gas constant is joule per mole Kelvin. It is on a molar basis. Okay, so they are different. Okay, so if we define compressibility factor Z in this way, PV over RT or PV bar, now volume is per mole and R is also per mole. This is universal gas constant. So they are equal actually. Both are per kilogram or both are per mole. So if we define it in this way for a gas. And if we plot, okay, here you see a rough plot. It is a plot of Z versus on the x-axis you have what is called reduced pressure. We indicate that as PR, reduced pressure, and this is defined as pressure over critical pressure. So for any gas, we know what is the critical pressure. So this is pressure over critical pressure. Okay. And similarly, we define reduced temperature. This TR is reduced temperature. And this is defined as temperature over critical temperature. Okay, so let me make it more clear for you to understand. So let us say for any gas, we have this data. Okay, we have pressure, volume, temperature data. Okay, so at a given pressure, what is its specific volume, what is temperature, we have this data. Now based on this data, we define Z is PV over RT. Okay, we know what is R for the gas if we know its molecular weight. So we have a column for Z and we have a column for PR. PR will be just divide this pressure with critical pressure. So we got this PR, and we also have a column for TR. TR is just divide this temperature with critical temperature. So you have a column for TR. And another column for this VR prime. I'm going to explain what this is. Okay, this also comes from this data. So you have a column for VR prime. Okay, and then we are just plotting this Z versus PR. Okay, you are plotting Z versus PR for different values of TR and see how that plot looks like for any gas. That plot looks like this. So when TR is 1, okay, TR is 1 means temperature equals critical temperature. Okay. So then this Z has this shape. It decreases and then it increases. Okay, if TR is 2, it has this shape. So if TR is 1.5, it will be in between. If TR is 3, it will be above this. So like that, we are plotting Z versus PR. Okay. And it turns out that it does not matter what the gas is. So it could be helium, nitrogen, oxygen, carbon dioxide, any gas. The data for all gases on this plot, on this Z versus PR plot, looks very similar. It is not exactly same, but the difference in data from different gases is few percent only, not more than 2-3%. So you can say that you can draw these representative curves, which you can say roughly represent all the gases. Okay, so this plot is called generalized compressibility chart. Okay, and on this plot we also have what is called this VR prime. It is defined as, it is called pseudo reduced specific volume. So unlike reduced pressure, you see reduced pressure was P over PC. Reduced temperature is T over TC. We can have reduced volume, which will be V over VC. Okay, but instead of reduced volume, we are using this pseudo reduced specific volume, which is defined slightly different. This VR prime, it is V over RTC over PC. Okay, and the curves for constant values of this pseudo reduced specific volume on this diagram, they look like this. So along this VR value is constant, say it's 0.1, 0.2, like that. And this chart you can find in the book. So that is generalized compressibility chart for any gas. And because it is same for all the gases, situation like this is called principle of corresponding states. Okay, it is an example of principle of corresponding states. So in the case of this diagram, okay, what you are saying is all gases look similar because the data for all gases is on the same plot and they look same. So you are saying that all gases look similar when you look at them in terms of reduced pressure and reduced temperature. So you are not looking at them in terms of pressure and temperature, but you are looking at them in terms of reduced pressure and reduced temperature, and then all gases look same. So this is an example of what is called principle of corresponding states. Okay. And on this diagram you see Z approaches 1 in two situations when this reduced pressure is very low. So regardless of temperature, Z approaches 1. So that is 1. Or if reduced temperature is high, it is above 2. Then also you see if reduced temperature is 3, you will get a curve around here, which will be very close to 1. Okay. So you get Z approaches 1 for any gas as reduced pressure is very, very less than 1, or reduced temperature is greater than 2. Okay. And if Z is 1, because Z is defined as PV over RT, you get PV equals RT. Okay, so you get PV equals RT, and this is the ideal gas law. So the gas is behaving as an ideal gas. So any gas, so I hope you understand this, there is no such thing as an ideal gas, but any gas behaves as an ideal gas when pressure is low or temperature is high. Okay, then it behaves as an ideal gas. And what do we mean by pressure is low? Is 1 atmosphere low, 2 atmosphere low, or 100 atmosphere low? What is meant by low pressure? We have to see in comparison to the critical pressure. So PR has to be low, then we say it is low pressure. TR has to be high, then we say it is high temperature. So it behaves as an ideal gas. We get PV equals RT. Okay. Okay. And there are different forms of this ideal gas law. Let me clarify those also, because we might end up confusing them. So PV equals RT. And in ideal gas law, this temperature is always in Kelvin. Don't take in Celsius. Okay. A different form of this equation will be, we can write PV over M, because specific volume is volume per unit mass, equals RT. And that gives you PV equals MRT. Okay, so there is a difference. Don't make this mistake. See, this is lowercase volume, so this specific volume, and this is total volume. With this, you have this M here. Okay. Okay, we can modify this further. You can write PV equals M, and instead of this gas constant, you can write universal gas constant over molecular weight times temperature. And then this becomes PV equals mass over molecular weight, that is number of moles. So that is N. N is number of moles. And this is universal gas constant, temperature. So this is a different form. Okay, so if you have number of moles here, this is universal gas constant. Okay. Now you can also do PV. Take this N on the left hand side. So PV over N equals R bar T, and this becomes P. Now this is volume per mole. So this is specific volume, but on molar basis. So you write that as V bar. Okay, equals R bar T. Okay, see, all of these are ideal gas law, same equation, but in terms of specific volume, gas constant, or universal gas constant, or specific volume on the molar basis. So don't confuse, you be consistent when you are using the equation. Okay. Okay, now, so just like we discussed that when V is constant, so the substance is incompressible, you get internal energy is a function of temperature only. Okay, that's the simplification, and based on this you get there is only one specific heat. We don't have to say Cp or Cv, and we get very simple result. Actually, same thing happens if PV equals RT. If a substance satisfies this law, so it behaves as an ideal gas, you get U is a function of temperature only. Okay, and it leads to actually lot of further simplifications. We are going to see that. And how we get this, the mathematical proof of this, it requires thermodynamic property relations. We will talk about that later on. But experimentally, there is what is called Joule's experiment, and he indicated that for an ideal gas, U is a function of temperature only. Based on an experiment, he indicated this. Because I'm going to briefly describe what that experiment was. So this is an insulated tank, and there is some liquid here. Okay, and he took these two bulbs which are connected with a valve. In one bulb there is a gas at low pressure. Okay, so it is at low pressure, means it will behave as an ideal gas, and other side is vacuum. Okay. And there is this means for measuring temperature here, and the whole thing is insulated. So the experiment was, when this valve was opened, because the other side is vacuum, now this gas is going to expand and it is going to fill both the bulbs, and he looked at what happens to the temperature, and he found that there is no change in this temperature when this valve is opened, no change in the temperature. So based on that, let us see how you can argue that U is a function of temperature only. So the observation was change in temperature is 0. That means that if I define this as the system, these two bulbs as the system, after opening this valve, there was no heat transfer from this bulb to the liquid here, because if there is any heat transfer, then this temperature will change. Okay, so this change in temperature is 0, means there is no heat transfer from this to this. Okay, and also there is no, for this system, I'm taking this as the system, when this valve is opened, there is no work transfer. Okay, because there is no electrical work, no boundary work, no shaft work, there is no work transfer. So there is no heat transfer and no work transfer. That means delta U is 0. Based on first law, delta U is Q minus W, so delta U is 0. Okay. But you see, when this gas is expanded, there is change in volume. Specific volume actually becomes twice. Okay. And there is change in pressure also. So there is change in pressure and there is change in volume, but still internal energy did not change, it remained constant. So then you can argue it means that internal energy does not depend on pressure or volume, it depends on the other variable which remained constant, which was actually temperature. Temperature did not change, so you can say U is a function of temperature only. So that is based on this Joule's experiment, but mathematically also you can show if PV equals RT, then U is a function of temperature only. Okay. And these are further implications of that. I'm going to show them in a while. Based on this, if U is a function of temperature only, we can show that Cv is du dt, Cp is dh dt, and Cp minus Cv is R. Okay, so let us do these. So if you do U is a function of temperature only, and Cv, which is defined as del U del T at constant volume, because U is a function of temperature only, this becomes du dt. Okay, or you can write du is Cv dt. Okay, now H is U plus PV, and for an ideal gas this becomes U plus, you see, PV is RT. Okay, PV is RT. Okay, okay, we are going to use this equation in a while. Let me also do the thing for Cp. Okay, yeah, so because U is a function of temperature only and R is constant and this is temperature, this means that H is a function of temperature only. Okay, for an ideal gas, H also is a function of temperature only. And Cp, which is defined as del H del T at constant pressure, because H depends only on temperature, this becomes dH dt. Or you can write dH is Cp dt. Okay, dH is Cp dt. Okay. Now we can use this relation further. H is U plus RT. If we differentiate this, you can write dH is du plus R dt. And dH is Cp dt. du is Cv dt. So dt cancels and you get Cp minus Cv is R. Okay, so these are very important relations. For an ideal gas, we must remember these. du is cv dt, u is a function of temperature only, and du is cv dt. H is also a function of temperature only, and both of these actually Cp and Cv also, because you see Cp is dH dt. This is also a function of temperature only. So these also Cp and Cv, they are function of temperature only. Okay, and you get dH is Cp dt, and Cp minus Cv is R. We get a relation between Cp and Cv. Or alternatively, you can write this in this form also. Cp bar minus Cv bar is R bar. Okay, this is on per unit mass basis, and this is on per unit mole basis. So what are the units of Cp, Cv and R? They have to be same units. You see, the definition of Cp was amount of heat addition, so that will be joule or kilojoule. Okay, per unit mass per kilogram, per unit rise in temperature, so joule per kilogram Kelvin. Okay, so here units of everything is joule per kilogram Kelvin, whereas in this case unit of everything is joule per mole Kelvin. Okay, it could be kilojoule or kilojoule, kilomole, that doesn't matter, but it's on a kilogram basis and this is on a molar basis. Okay, okay. And we also have this K, that is the ratio of specific heats, and it is defined as Cp over Cv, or you can write as Cp bar over Cv bar. Okay, means the same thing, you'll get the same ratio, that is K. So now, okay, one thing you understand is, because Cp is a function of temperature only, Cv is also a function of temperature only, this K is also a function of temperature. Okay. So you will find these tables in the book where for different gases you'll have temperature versus Cp, Cv and K values. Okay, you can see in the appendix, I'm not going to show you, but with temperature the value of Cp, Cv and K, those are given. And out of these three, Cp, Cv and K, only one is independent. Okay, from Cp, Cv and K. Only one is independent and others are dependent. We can find out. So if you have one of these, you can determine others. Let me show you that. Based on these relations, we have Cp minus Cv is R. Okay, again, this is true for an ideal gas. And we have Cp over Cv is K. Okay, so based on these two relations, if you have, let us say you have the value of K, then based on these two relations you can determine Cp and Cv. You will get Cv will be R over K minus 1 and Cp will be Kr over K minus 1. See, that is right. Yeah. Okay, so if you have value of K, you can determine Cp and Cv both. If you have value of Cp, then also based on these two relations, okay, based on these two relations you have Cp, you can determine Cv and K. So you have to know only one of Cp, Cv and K, and others we can determine. Okay. Okay, so let us also see how these specific heats Cp and Cv vary with temperature for an ideal gas. So variation in Cp of ideal gases with temperature. Okay, I'm going to show you one plot. Okay, let's see if this is visible. Okay, it is not going to be very clear actually. But what I have here is, in this plot, this is from the textbook. On the x-axis it has temperature. Okay, x-axis is temperature and y-axis is Cp over R. So this is non-dimensional because the dimension of Cp is same as dimension of R. So Cp over R is non-dimensional. And you look at how Cp over R changes with temperature for different gases. This is for CO2, this is for water, for oxygen, hydrogen, and this below here is for monoatomic gases. Actually, better is I just draw and show you. So if we have, this is Cp over R. Okay. So, and if we plot this with temperature for different gases, you get these curves. For monoatomic gases, it does not change with temperature. This is for monoatomic gases like helium, neon, argon. These are monoatomic gases. For these gases, this value is Cp over R is 5 by 2 and it remains constant. It does not change with temperature. For other gases, take diatomic gases like oxygen. It increases with temperature. So you have behavior like this. It increases with temperature. Okay, so this is for diatomic gases like oxygen. Okay, if you have further complex molecule like CO2, which is triatomic, then its value is even higher. Okay, so one idea is as molecule becomes more and more complex, this is monoatomic, these are diatomic, these are triatomic. As it becomes more and more complex, its Cp increases, or you can say its energy storage capability increases, thermal energy storage capability, because Cp is a measure of thermal energy storage capability. And it increases because it is more complex. It can store energy in extra modes which are not available to simpler molecules. Okay. And other thing is for monoatomic gases, it remains constant. It does not change with temperature. Whereas for other gases, for diatomic or polyatomic gases, it increases with temperature. So that is the trend. And this you can also remember that for monoatomic gases, Cp over R is 5 by 2. Or alternatively, you can say Cp bar over R bar, same thing. Okay, you have to be consistent. Both of these are on per mole basis. This is also 5 by 2 for monoatomic gases. Okay, for monoatomic gases. Okay, yeah. Now let us see how to get change in enthalpy and change in internal energy for ideal gases. I already showed you that you get du is CVDT. Okay, So what will be delta U? If we integrate this expression, say between 1 and 2, then delta U is integral Cv dt, because Cv is a function of temperature. Okay. Now there are two possibilities. One is I take Cv at some average temperature. Because temperature actually goes, say, from T1 to T2. So I'm taking Cv at some average temperature, because it varies with temperature. I can take a value which is at the midpoint of 1 and 2. Okay, and then take it outside of integral and approximate delta U as Cv, which is at average temperature, times change in temperature, Cv delta T. Okay, that is one option I have. And we use this option very often. Okay, so if the problem says that take specific heat as constant, it means we are going to use this one. Okay, because we take it outside of integral, it will be Cv delta T. Or if in the problem, if we are given value of K, Cp or Cv. Okay, if one of these are given, because you see in reality all of these are functions of temperature. But if value of one of these is given, that means implicit in that is it is saying treat this as a constant. So you are going to do the same thing. If you know one of these, you can determine all others. I already explained that. Okay, so we are going to find change in internal energy in this way. Okay, that is one option. And we can do the same thing for change in enthalpy. We already derived this expression that dH is Cp dt for an ideal gas. If I integrate this, okay, and I'm taking Cp at some average temperature, then after integrating that, you can write delta H is Cp delta T. Okay, so what we did with internal energy, we do the same thing with enthalpy. That is one option. Okay. Okay, other option is we retain it as it is. So we are keeping dH is Cp dt, and then we are writing, say, enthalpy at any temperature T, okay, minus enthalpy at some reference temperature. So we integrated this expression from Tref to T. So this will become enthalpy at T minus enthalpy at Tref equals integral Cp dt from Tref to T. Okay, and the choice of Tref is arbitrary. Okay, okay. Further, what we can do is, let us say we take that this Tref is 0 Kelvin. It is arbitrary, but if we take that choice and we take that enthalpy at this reference temperature is 0. Okay, we have to give a reference state. It is arbitrary because eventually we are interested in change in enthalpy. So if we do that, okay, then you get enthalpy at temperature T is integral from 0 to T of Cp dt. Okay. And this integral has already been evaluated for us and is available in the form of tables. Okay, so we did not make any approximation of constant Cp or average Cp here. We just kept it as it is, but it has been evaluated for us. And similarly, you can also get internal energy at temperature T, which will be just enthalpy minus, okay, RT, because enthalpy is U plus PV and PV is RT, so U will be H minus RT. Okay, so we get that also. And in the textbook, these tables are available for different gases. You'll find these tables as a function of temperature. Okay, what is enthalpy and internal energy, okay, for different gases. So one option we have is corresponding to a given temperature. We can read the value of enthalpy and internal energy directly from here. Okay, and say I have to find change in enthalpy between say temperature T2 minus temperature T1. So corresponding to T1 and T2, I can read enthalpy from the table directly, and that will give me the change in enthalpy or change in internal energy. Okay, that is one option. Other is we use the value of Cp, and change in enthalpy is Cp delta T, and change in internal energy is Cv delta T. We can do that. Okay, so that is for ideal gases. Okay, so let me summarize these results for ideal gases, and these we must remember. We get internal energy, enthalpy, Cp, and Cv. All of these are functions of temperature only. Okay, for an ideal gas. Okay, further you get dH is Cp dt. We can integrate these to get delta H is Cp delta T. And we get du is Cv dt. And you get Cp minus Cv is R. Okay. And you also get Cp is Kr over K minus 1, and Cv is R over K minus 1. Okay, so these we must remember. Okay. And again, for monoatomic gases, you will not find any tables for U and H. There are no tables for U and H because we don't need those tables. See, for monoatomic gases, specific heat is a constant. Cp is 5 by 2R. It is a constant. Okay. So we have, if we have to find change in enthalpy, dH is Cp dt. It is 5 half R dt. So this is a constant anyway. We don't need any table. So you get change in enthalpy will be 5 half R change in temperature. Okay, so we don't need any table. Okay, and du is Cv dt. Cv will be 3 by 2R because Cv will be Cp minus R. So 5 half R minus R, that is 3 half R dt, and you integrate this, you get delta U is 3 half R delta T. Okay. And another thing you must note is in these equations, you see this is lowercase h. This is change in specific enthalpy, change in specific internal energy. So if you want to write dH, this is change in total enthalpy. You have to multiply it with mass. It will be mCp delta T, mCp dt. Okay. Similarly, du will be mCv dt. Okay, this is per unit mass basis. Units have to be consistent. This is joule per kilogram Kelvin, joule per kilogram, sorry. And this side is also joule per kilogram. Here this is joule, and this side is also joule. They have to be consistent. Okay. Okay. Let us see. Okay. Now, when to use these ideal gas equations? Okay, all these ideal gas law, that is PV equals RT, and all these equations for internal energy and enthalpy. Let us say the problem says it is steam. Can we use ideal gas law? Or if it says it's oxygen or it is nitrogen, can we use ideal gas law? Actually, ideally, okay, what we should do is first determine Z from the compressibility chart, from the generalized compressibility chart corresponding to the uh, state that is given. Let us say pressure and temperature are given. Okay, for oxygen or any other gas, pressure and temperature are given. First, we can determine reduced pressure and reduced temperature, and based on these, we can read the value of Z from the generalized compressibility chart. And if Z turns out to be 1, that means you can use the ideal gas law. And if it is not 1, then you can't use ideal gas law. Okay, you have to read all the values from the tables, from the property tables. You can't use ideal gas law and all the other laws. Okay, so that is the way ideally we should do. But in reality, while solving problems, we don't even have sufficient time to first determine Z and then see. So in this particular course, whenever you have all these gases, say oxygen, nitrogen, argon, helium, or air, or carbon dioxide, okay, all these gases, then in this course, by default, the state is such that if you determine Z, it is going to be 1. Okay, numbers are given in that way, it is going to be 1. So we can safely use the ideal gas law. Okay. Or alternatively, the problem will say that you can use the ideal gas model for this situation. Okay. But if it is, say, water vapor, okay, or say some refrigerant vapor, or say ammonia. Ammonia is also a refrigerant. So ammonia. Okay. Most likely the situation is going to be such that Z is not 1 if we actually calculate this. So don't use ideal gas law. Okay, but read all the properties, this pressure, volume, temperature, or internal energy, enthalpy, all these things from the table. Okay, so that is the question. So this ideal gas law makes life very easy in terms of solving the problem, but we have to be very cautious while using this. Okay, and it turns out that on the temperature volume diagram, okay, this is vapor dome. Actually, this is the region in which you get maximum error by using ideal gas law. Okay, you get maximum error by using ideal gas law. Okay, in this region, it is fine. In this region, it is fine. Okay, because see, in this region, actually pressure is low. Okay, so it behaves as ideal gas, and as you are going in this direction, you have low pressure and also high temperature, so ideal gas law is valid. But close to critical point and in this region, ideal gas law is not valid. And when we are dealing with steam turbine or cycles where water is the working fluid, the situation is going to be in this region, so don't use ideal gas law. And when we are dealing with refrigerants, refrigerant vapors are also going to be in this region, so we are not going to use ideal gas law. Okay. Okay, this is the last topic I'm going to talk about, and then we are going to do several problems. Uh, this is what is called a polytropic process. Okay. Polytropic process is defined as PV to the n is constant. If during a process PV to the n is constant, what it means is P1, you can write specific volume or total volume, does not matter here. It's a closed system. P1 V1 n equals P2 V2 n. If that is the process. Okay, during the process, this term remains constant. Then it is called a polytropic process. And for this process, if we evaluate boundary work, we get this expression P2 V2 minus P1 V1 over 1 minus n if n is not equal to 1, and PV log V2 over V1 if n equals 1. So I'm going to derive these expressions. Okay, so for a polytropic process, that is PV, n is constant. Let us first see how this process looks like on a pressure volume diagram. If I differentiate this after taking log, like I can first write log P plus n log V is log C. And now I differentiate this, it becomes dP over P plus n dV over V is 0. And you get dP dV is negative n P over V. Okay, so this gives the slope because dP dV is the slope on the pressure volume diagram. Okay, dy dx, that's the slope, is negative n over np over v. Okay, now take different situations. If n is 0, that means the process is constant pressure process. Okay, so it will be like this. If n is infinity, then see the slope will become infinite. dP dV will be infinity. So the process is like this. It is a constant volume process. Okay. If n is 1, the equation gives us PV is constant. That is actually a hyperbola. On the pressure volume diagram, PV constant is a hyperbola. It will look like this. If I want to draw through from this point, PV is constant. It will go like this. This is n is 1. Okay, if n is greater than 1, then you see if n, the slope is negative np over v. So at this point, if n is greater than 1, it will be steeper. It is the slope is negative, but it will be steeper. So it will be like this. Okay, from this point, okay, this is say n is greater than 1. Okay, so that is how this process looks like on the pressure volume diagram. Okay, and when we want to evaluate boundary work for this process, boundary work is integral pdv, and if the process is from 1 to 2, you can write this as, because pv to the n is constant, so p is c over v to the n. Okay, c over v to the n dv from 1 to 2, and c is a constant, so this comes outside of integral, and the integration of rest becomes v to negative n plus 1 over negative n plus 1, and we'll have term here v2 negative n plus 1 minus v1 negative n plus 1. Okay. And instead of this c, you can write P1 V1N or P2 V2N, because see, this C is PV to the N, so you can evaluate this at 1 or at 2. This PV to the N remains constant throughout. So when we distribute this C with the first term, I'm going to write P2 V2N, and when we distribute this with the second term, I will write P1 V1N, and you just substitute them, and you get is, you'll get WB is P2 V2 minus P1 V1 over 1 minus N. Okay, so you should, this is fairly easy. If you are given any process and you have to evaluate boundary work, then all you need is, you have to express pressure in terms of volume and then do the integration. Okay, so that is boundary work for a polytropic process when N is not equal to 1. And when N equals 1, then say what you have is PV is constant when N is 1. Okay, and you do the integration. I'm not going to do that, but you will get, it will actually be PV log V2 over V1. Okay, you'll get this answer for boundary work when N is 1 or PV is constant. Okay. And for this PV here, you can write P1 V1 or P2 V2, because both will be equal, because PV is constant, it can be P1 V1 or P2 V2. So that is boundary work here. And these equations are valid for any substance, because if the process is PV to the N is constant, we did not say what the substance is. These are valid for any substance. A special case is when the process is polytropic. And the substance is also an ideal gas. Okay, then we can reduce these equations further. Instead of P2 V2, you can write MRT2 using ideal gas law. This will be MRT1. So you can also write these, that boundary work will become MR T2 minus T1 over 1 minus N. Okay, you can do that. And you can divide this equation with M, and this will become lowercase w. So this is work, this will be work per unit mass. So we are going to use lowercase symbol for that. This will be R T2 minus T1 over 1 minus N. So if it is also an ideal gas along with being polytropic. And similarly, this PV equals constant. If it is an ideal gas, this is actually an isothermal process. You see, PV equals MRT, and if PV is constant, it means temperature is constant. Okay, if the substance is ideal gas, so it is an isothermal process. So the boundary work for an isothermal process for an ideal gas, that will be same what we derived here, PV log V2 over V1. Or you can further use ideal gas law. Instead of this, you can write MRT log V2 over V1. So there you can manipulate it further using the ideal gas law. Okay. And one final thing is, again, if it is polytropic and also ideal gas, then this relation, you see, PVN is constant. That is polytropic and it is also an ideal gas. Okay. Then we can manipulate it further. I'm going to show you that. We can, along with this, if we use PV is RT, I can eliminate P from these two equations. We get P is proportional to T over V. R is a constant anyway. So instead of P, you can substitute temperature over volume, and this constant will be some other constant now. Okay, so by manipulating this, you will get TV to the n minus 1 is constant. So these constants are not same. So to avoid confusion, if this is C1, this is some other constant. But what basically this means is T1 V1 n minus 1 equals T2 V2 n minus 1. Okay, that is what we care. So this equation is same as P1 V1 n equals P2 V2 n. Okay, because we manipulated this equation by using ideal gas law and we got this. So if it is polytropic and also ideal gas, we can use this. Or we can eliminate volume from this equation by using ideal gas law, and you will end up with this equation. Let me see, you will get volume is T over P. You will get P1 1 minus N T1 N equals P2 1 minus N T2. Okay, this equation. So these three equations are identical. This polytropic process, if it is also an ideal gas, instead of using this equation, we can use this or this. They are identical. But this equation is in terms of pressure and volume. This is in terms of temperature and volume. And this is in terms of pressure and temperature. So the use of one of these will be easier depending on what is given. Okay, so that's the idea. Okay, so we are done with the theory here, talking about ideal gases and how to get change in enthalpy, change in internal energy for ideal gases, and this boundary work thing. I'm going to do several problems on these now. Okay. Let us look at this 20G. Okay, it says a balloon containing an ideal gas. So it's an ideal gas is initially kept in an evacuated and insulated room. And the balloon ruptures and the gas fills up the entire room. Which one of the following statement is true at the end of the above process? And it says if the internal energy and enthalpy, if they remain constant, they increase or they decrease, what happens? This is a gate question. So what you have is, so in an insulated room, there was a balloon and the room is evacuated. There was vacuum here and balloon ruptures and this gas fills the entire room. Okay, actually this situation is similar to the Joule's experiment. Okay, but let me also illustrate one more thing here. So when this gas expands, when balloon ruptures, see, let us say at any instant, this is the envelope inside which there is gas. Okay, so there is still vacuum here, but the gas has expanded, so it is in this region now. And as its volume is increasing, as it is expanding further, is this system, if we take this as the closed system which includes all the gas, is it doing any work on the surrounding? Okay, because its boundary is moving. See, this boundary is moving, the system boundary, and we have boundary work as integral PdV. Okay, so you may wonder, volume is increasing and there is some pressure, so it is doing some work on the surrounding. Okay, actually that is not true. There is no work being done on the surrounding. This is an example of, this is not a quasi-static process. This is not quasi-static process, this is unrestrained expansion. So So this gas is expanding and there is no pressure here, there is vacuum. So there is nothing that is opposing it. And in the equation for boundary work, see, boundary work is integral PdV. If it is not a quasi-static process, this pressure P is pressure at the boundary that is moving. Okay, and pressure at the boundary right here, actually that pressure is zero because there is vacuum here. Okay, so there is no boundary work in this case. Okay, so if you take this as the system, it expands, there is no boundary work, and there is no heat transfer also, everything was insulated, so there is no change in internal energy. Okay, no change in internal energy, that means there is no change in enthalpy. Delta H is also zero because both of these are functions of temperature only. If one is constant, other is also constant. Okay, so U and H both remain unchanged in this case, and there is no boundary work involved. Okay, let us look at 21. This is also a gate problem, and it says for an ideal gas with constant values of specific heats. So it says that specific heats are constant. Okay, they are not given as functions of temperature. For the calculation of specific enthalpy, so the lowercase h, what do we need? It is sufficient to know only the temperature, or both temperature and pressure are required, temperature and volume are required, or temperature and mass are required. Okay. See, for an ideal gas, when we talk about enthalpy, what is important is temperature. Pressure and volume, those are not even important. So you need temperature. And it says specific enthalpy, then we don't need mass because specific enthalpy is per unit mass. So the answer will be A. If we have to tell total enthalpy, then we have to know temperature and also mass. Okay, then the answer will be D, but now answer is A. So these were just some conceptual problems. Let us see 22G. This is also a gate problem. Say a 2 kilowatt 40-liter water heater is switched on for 20 minutes. Okay, it doesn't give us the type of container, whether it is constant pressure or constant volume. I'm just going to take a container, and in this there is 40-liter water and a 2 kilowatt heater is turned on for 20 minutes. So that is the heat transfer to this. The heat capacity Cp for water is 4.2 kilojoule per kilogram Kelvin. Actually, this number you can remember also for water because it is such a common fluid. For water at room temperature, its specific heat, and see, it is incompressible. We are talking about liquid water here. It is 4.2 kilojoule per kilogram Kelvin. Okay. Assuming all the electrical energy has gone into heating the water, so there is no heat loss. Increase of water temperature in degrees centigrade is, so what is the change in temperature of water? So we apply first law, which is delta U is Q minus W. There is no work, and this delta U you can write as, we are taking water as incompressible. Okay, and actually this work is zero is true if the process is constant volume process, because I'm making this assumption it is a constant volume process. Okay, now this delta U, which is M delta U, and taking water as incompressible, delta U is C delta T. For an incompressible substance, it is C delta T. So it will be M C delta T. equals Q. And now we can just substitute numbers. Delta T is Q over MC, and Q, it's 2 kilowatt heater. I'm converting that to watt. So 2000 watt, and it is on for 20 minutes. That is 20 times 60 seconds. So this is heat transfer. Okay, watt times time. This is heat transfer. Over mass of water, it's 40 liter, and 1 liter is 1 kilogram. Okay, so it's 40 kilogram. Times specific heat is 4.2 kilojoule per kilogram Kelvin. So that is 4200 joule per kilogram Kelvin. So you just do the calculation, you get 14.3 degrees C. Okay, so in this case we treated water as incompressible, and we wrote delta U is C delta T. Okay, but don't forget this M for the uppercase delta U. Okay, let us see number 23. This is also a gate problem, and it says temperature of nitrogen in a vessel of volume 2 cubic meter. Its volume is 2 cubic meter. Temperature is 288 Kelvin. A U-tube manometer connected to the vessel. A U-tube manometer is, it's like this. You know from fluid mechanics about this. Okay, it is open on this side and it is connected here. It shows reading of 70 centimeter of mercury, level higher in the open end to atmosphere. So it is like this. So if mercury is like this here, then the level is higher on the open side, and this distance, okay, this is 70 centimeter. The universal gas constant is 8314 joule per kilomole Kelvin. Okay, so units here are given different. 8314, it is 8.314 joule per mole Kelvin, but it is joule per kilomole, so becomes 8314. Okay. And atmospheric pressure is given this much bar. Acceleration due to gravity is 9.81, and density of mercury is 13600. The mass of nitrogen in the vessel is, we have to determine the mass of nitrogen. Okay, so nitrogen under these conditions, it is going to behave as an ideal gas. Okay, so we just use ideal gas law. So PV equals MRT. Okay, ideal gas law has different forms, so make sure if this is V, this will be M, and this is gas constant. So M is PV over RT. Now volume is given 2 cubic meter, temperature is 288 Kelvin. We need gas constant for nitrogen. Okay, this is not universal gas constant, this is gas constant for nitrogen. And the gas constant for nitrogen will be universal gas constant over molecular weight of nitrogen. And that will be, universal gas constant is 8.314 joule per mole Kelvin. Molecular weight of nitrogen is 0.028 kilogram per mole. 28 gram per mole or 0.028 kilogram per mole. So we should know that. Okay, so we get, this is gas constant for nitrogen. This is what will go here, and the units here are joule per kilogram Kelvin. Okay, so we have R, temperature, volume, we need pressure, then we can apply this equation and get M. Pressure will be okay, based on manometers. You know that from fluid mechanics. Pressure here will be atmospheric pressure plus pressure due to this column of mercury. So this will be atmospheric pressure plus pressure due to mercury column, that will be rho GH. Okay. And atmospheric pressure is 1.01325 bar. Okay. You have to convert this to Pascal. So times 10 to the 5, that is Pascal. That is atmospheric pressure plus rho GH. Density of mercury is 13600 times, okay, I'm doing it here, G is 9.81, and this height of this column is 70 centimeter, that is 0.7 meter. Okay. So this is the pressure you get in Pascal. Pressure in Pascal. I should change the zoom. Okay, so now we can substitute numbers in this equation and be consistent with units. When using this equation, I'm writing it here again. So M is PV over RT, and see the units. If pressure is in Pascal, volume is cubic meter, R is joule per kilogram Kelvin, and temperature in Kelvin, then mass is in kilogram. Okay, so be consistent with units. So we have all the numbers, you just plug numbers, and that gives M is 4.7 kilograms. So in problems like this, you can make a mistake of confusing gas constant with universal gas constant, or in changing the in taking proper units for pressure, and then you won't get the right answer. Okay, let us look at number 24. This is also a gate problem. Actually 24 is very simple. I'm just going to skip to 25. This is also a gate problem. Okay, it says work is done on an adiabatic system due to which its velocity changes. There is an adiabatic system uh, and its velocity changes from 10 to 20 meter per second. Elevation changes increases by 20 meter. So elevation we indicate as Z. So it increases by 20 meter. And temperature increases by 1 Kelvin. And change in temperature is 1 Kelvin. The mass of the system is 10 kilogram and CV is 100 joule per kilogram Kelvin. And the value of G, gravitational acceleration, is given as 10 meter per second square. It says if there is no change in any other component of the energy of the system, the magnitude of total work done in kilojoule on the system is. So we have to determine work done in kilojoule on the system. Okay, so again, this is just first law. Delta U is Q minus W. Okay, is this right in this case, this equation? The problem says the system is insulated, so Q is 0. That's fine. but delta U equals Q minus W. Actually, this is not right. The system given here is not a stationary system. So the general situation is you write delta E is Q minus W, and where this delta E is delta U plus delta KE plus delta PE. And only for a stationary system you get these kinetic energy, potential energy changes zero, so you get delta U is Q minus W. So you have to be careful. In this case it is not stationary. Okay, so now we just have to apply this equation, and Q is 0, so just plug numbers. See delta U, and it gives it was an, what was the substance in the problem? Let me see. It gives CV, but it doesn't say. So this delta U will be mCV delta T. So I'm just writing that it will be mCV delta T. And change in kinetic energy will be half m v2 square minus v1 square. Okay, this is velocity, this is not volume. Plus change in potential energy will be mg times change in elevation, and this equals negative W. Okay, so all these values are given to us. We have CV, change in temperature, V1, V2, G, delta Z, M, everything is given. So you just have to plug numbers in this. But again, when we are adding these things, we have to be consistent with units. So if velocity is meter per second, so see this V square will be meter square per second square. Okay, then this CV, okay, don't have a, should not have any kilo there. It will be joule per kilogram Kelvin. Okay, it will not be kilojoule per kilogram Kelvin, because this is based on meter and second. There is no kilo here, so there cannot be any kilo here. It will be joule per kilogram Kelvin, and similarly units here, so you get work here. Okay, so the answer you get is, you get W is negative 4.5 kilojoule, but the problem says you have to tell the work done on the system. Okay, and work done on the system is negative. That is the sign convention for work. So work done on the system, okay, is 4.5 kilojoule. Okay, turned out to be negative. So that means this is the work done on the system. Its magnitude is 4.5 kilojoule. And let me clarify one thing about specific heat. I did not mention that previously. See, for specific heat like Cp and Cv, joule per kilogram Kelvin is same as joule per kilogram degree C. Okay, because see this Kelvin or degree C here, they correspond to change in temperature. They don't correspond to temperature, they correspond to change in temperature, because specific heat is amount of energy required per unit mass per unit change in temperature, and change in temperature is same whether you take in Kelvin or in Celsius. Okay, so don't try to add the 273 thing here and confuse. It is going to be same. Okay, let us look at number 26. This is also gate problem. Okay. It says a well insulated rigid container rigid container insulated of volume 1 cubic meter. It contains 1 kilogram of an ideal gas. So it's an ideal gas. And we are given Cp and Cv. at a pressure of 10 to the power 5 Pascal. A stirrer is rotated at a constant RPM. There is a stirrer here, and it is rotated for 1000 rotations. Okay, 1000 rotations. And the applied torque is 100 Newton meter. I'm using symbol T for that. This is not temperature now, or let me use some other symbol, say T prime. Okay, this is torque. This is 100 Newton meter. The final temperature of the gas in Kelvin is, so final temperature, let us call that, say, T2. So again, for this system, there is interaction between surrounding and system. We can just apply first law for a closed system. That will be delta U equals Q minus W. Okay. And now we are going to expand these terms. The substance is ideal gas. For an ideal gas, what is delta U? And we are given the value of Cp and Cv. Okay, so that means the problem says use constant specific heat. So delta U is m Cv delta T equals Q. Q is 0 because it is insulated, there is no heat transfer, minus W. There is no boundary work, but work is done by this stirrer. Okay. And we are given torque. Torque is this much, and it undergoes 1000 rotations. So the amount of work done when you have a torque and rotation, the amount of work involved will be this torque times theta. So that is work done. This is same as force times displacement. That is the work. But here we'll have torque times theta. Okay. And don't forget the negative sign because this is work done on the system. So this becomes torque times theta. T. And theta, okay, because number of rotations are given, we will be able to write that theta. Okay. Now let us see what is given. We have Cv, this is given. Torque is given. We can determine theta because number of rotations are given. We don't have, okay, m is also given 1 kilogram. So this gives us change in temperature, delta T. So let me write that. So change in temperature becomes, the torque is 100. Theta will be 2 pi times number of rotation, 1000 rotations. Over mass is 1 kilogram. And Cv is given 800 joule per kilogram Kelvin. Okay, so again be consistent with units. If torque is Newton meter, this is 2 pi number of rotations, mass is kilogram, then this Cv will be joule per kilogram Kelvin. Don't take kilojoule here. So this gives us delta T, which is T2 minus T1, final minus initial temperature. Okay, we still need initial temperature to get final temperature. So for that we can apply ideal gas law, which will be PV equals MRT. Okay, and we are applying this at state 1. So let me write P1V is MRT1. Okay, so don't forget this mass is constant, volume is constant, so we don't have to use subscripts there. Now say this T1 will be P1V over MR. P1 is 10 to the power 5 Pascal. So we are taking that in Pascal. Volume is 1 cubic meter over M. M is 1 kilogram. And we need R. This is gas constant. But look at the problem. You see, the problem doesn't even say which gas it is. It just says an ideal gas. Okay, it's an ideal gas, and how to get its gas constant. Actually, if you see, it gives values of Cp and Cv both. And for an ideal gas, Cp minus Cv is R. Okay, so R is 1000 minus 800, that is 200 times 200. So this gives T1 and you plug the number here, that will give you T2. The answer you get is the final temperature is 1285 K. So see, in a problem like this, you can be tested several concepts. You have to apply first law and then also know about the ideal gas and ideal gas law, and also the Cp minus Cv is R, that sort of thing. Okay. Okay, let us see number 27. This is also a gate problem. It says a football was inflated to a gauge pressure of 1 bar. Well, let's say this is football, and it is inflated to gauge pressure of 1 bar. So if gauge pressure is 1 bar, the absolute pressure, because atmospheric pressure is 1.01 bar, it is 2.01. You are adding atmospheric pressure to the gauge pressure. So this is the pressure. It was inflated to this pressure. When the ambient temperature was 15 degrees C, that means the temperature of the air inside, okay, everything is 15 degrees C. Okay, so those are the conditions of this football. When the game started next day, the air temperature at the stadium was 5 degrees C. So next day air is at 5 degrees C, that means football also, it will be in thermal equilibrium, it is there, so it is also at 5 degrees C. So next day temperature of football is 5 degrees C. Assume that the volume of the football remains constant at 2500 cubic centimeter. So it's a constant volume situation. Okay, its volume remains constant. Okay, now we have to determine the amount of heat lost by the air in the football. Okay, because its temperature changed from 15 to 5, amount of heat lost, and the gauge pressure of air in the football at the stadium. Okay, so we have to find its final pressure. You see, it's P2 gauge and amount of heat lost by the air, and Q. So we have to apply first law. It's a closed system. Delta U is Q minus W. There is no work involved because it is constant volume. Okay, so boundary doesn't move. So this term is 0. So Q is delta U. Okay, and it is an ideal gas. Okay, air is an ideal gas at these conditions. So delta U will be M CV delta T. Okay, this is uppercase U, so don't forget this M. It will be M CV delta T. Okay, let us see what is given. Delta T is given. M we need to determine because we have pressure, temperature, and volume. Based on these, we can determine M. So based on ideal gas law, M will be P1 V over R T1. Okay, and I'm evaluating at state 1, and because V is constant, M is constant, I don't have to say 1. P1 V over R T1. No, substitute numbers. In this equation, this pressure has to be absolute pressure. It is not gauge pressure. When we are using ideal gas law, pressure is absolute pressure. Okay, so this will be 2.01 bar, but convert this to Pascal. 2.01 times 10 to the 5, that is Pascal. Okay, volume is 2500 cubic centimeter. You have to convert this to cubic meter times 10 to minus 6 cubic meter. So PV, R for air, okay, gas constant for air. This will be molecular weight, sorry, universal gas constant 8.314 over molecular weight of air. You see, air is a mixture of mostly oxygen and nitrogen. and molecular weight of oxygen is 32, nitrogen is 28 gram per mole, and air is in between. So this number for air, you must remember that molecular weight of air is 28.97 gram per mole. That becomes 0.02897 kilogram per mole. Okay, let me write here. Molecular weight of air is 28.97 gram per mole. Okay, so 0.02897 kilogram per mole. We are being consistent with units here. R, and temperature, that is 15 degrees C, so that becomes, you add 273, so it becomes 288 Kelvin. Okay, so pressure is in Pascal, V in cubic meter, this gas constant, again consistent units, and temperature in Kelvin. So we are going to get M, whatever number you get, in kilogram. Okay, so now we have M, and Q we have to determine. So just use this equation. Q is M. We already got that from here. I don't have the answer, but you have this number with you. And C, V for air. Actually, in this problem, it is not even given. Okay, it is not even given. Okay, so another thing that you can remember, few things we have to remember. Molecular weight of air, you remember. Okay, you can remember Cp of air at room temperature. It is a function of temperature. Cp is a function of temperature, but at room temperature, it is 1.005 kilojoule per kilogram Kelvin. So it is close to 1. Okay, it is good to remember this number, Cp for air. Okay, but in this equation we need Cv, but Cv is Cp minus R, so I can use that. So Cp, which is 1005. Okay, I am using joule per kilogram Kelvin here, minus R. R is 8.314 over 0.02897. Okay, so this is Cv for air. Cp minus R, that is Cv. So M Cv, and change in temperature was 10. 15 minus 5, that is 10. So you get the answer here. So this Q is, you get 43.7 joule. So that is Q. And we have to also determine this final pressure in gauge. Okay, P2 in gauge. So let me write like this. Because it is an ideal gas, you can write P1 V1 over T1. What is this equal to? This equals Mr. Okay, because PV is MRT, that is ideal gas law. So PV over T is Mr. And similarly at state 2, you have P2 V2 over T2 equals Mr, because P2 V2 is MRT2. So effectively, if it is a closed system, you have an ideal gas, so you write PV over T is a constant. P1 V1 over T1 is P2 V2 over T2. We can use that ideal gas law here. So in this case, volume remains constant. Okay, so I'm not using this now. Volume remains constant, so that cancels. So P2 will be just P1 T2 over T1. Okay, P1 was 2.01 bar, 2.01. T2 we have to take in Kelvin, that is 278, and T1 is 288. Okay, this gives us P2, but we want P2 gauge. P2 gauge will be P2 minus atmospheric pressure. This answer here is in bar, because I retained pressure P1 in bar, this is in bar, so minus atmospheric pressure 1.01 bar, you'll get actually 0.93 bar. Okay, so that is P2 in gauge. Okay. There is another part to this which says gauge pressure of air to which the ball must have been originally inflated so that it would be equal to 1 bar gauge at the stadium. Okay, so at what pressure it should have been inflated to get 1 bar gauge at the stadium? We just apply ideal gas law, what we did right now, which was, see, you have this relation P2 over T2 is P1 over T1. Okay, and now just plug numbers in this. We want P2 to be 1 bar gauge, so absolute value of P2 will be 2.01, 1 plus 1.01. P2 we want is 2.01, and T2 is 5 degrees C. Okay, so that will be 278 Kelvin equals P1 over, this is 15 degrees C, that is 288. So that gives us P1, and if we want P1 gauge, that will be P1 minus atmospheric pressure. Okay, so you do that and the answer you get is 1.07 bar. Okay, okay, so these problems are on ideal gas. Okay, let us look at number 28. This is also a gauge problem. Okay, it says a cylinder contains 5 cubic meter of an ideal gas at 1 bar. 5 cubic meter ideal gas at 1 bar. This gas is compressed in an isothermal process. Okay, so the process is given till its pressure increases to 5 bar. The work in kilojoule required for this process is. So let me write down what is given. Okay, so its volume is 5 cubic meter, but that is its initial volume. Because it is compressed, we have to use V1, V2 like that. And its initial pressure is 1 bar. And its pressure increases to 5 bar. It's an ideal gas. And the process is isothermal. Isothermal means temperature remains constant. The work in kilojoule required for this process is. Okay. So you know it's a closed system, boundary work is integral PdV. Okay. And ideal gas, which is PV, equals MRT. So if temperature is constant, that means the process is PV is constant. Okay, so PV is constant. So for this process, PV is constant. You integrate integral PdV, you get boundary work is PV log V2 over V1. Okay, PV log V2 over V1. And you can write it in different ways by using ideal gas law. You can also write this as PV log P1 over P2. Okay, because see, you have P1 V1 over T1 equals P2 V2 over T2. Okay, both of these are MR and it is a constant temperature process, so T1 and T2 cancels. So the ratio of volume equals ratio of pressures, but reciprocal of that. V2 over V1 is P1 over P2. Now we can plug numbers. So PV, we are given pressure at 1 and volume at 1, so we can use that combination of PV. We can use P1 V1 or P2 V2. We just use PV directly. Pressure is 1 bar. That will be 10 to the power 5 Pascal. Okay, volume is 5 cubic meter. V log P1 over P2. P1 is 1, P2 is 5, 1 over 5. So you evaluate and you get negative 804,700 joule. Okay, your answer will be joule because we did not use any kilo here. This was cubic meter, this was Pascal. So answer will be in joule. Or you can say negative 804.7 kilojoule. Okay, but the problem says work required. So work required is 804.7. Okay, this negative sign indicates this was work done on the system. So if you have to say how much is work required, it is 804.7. So that's 28. Okay, let us look at 29. I'm going to do 4 or 5 more problems. It gives a piston cylinder device contains 0.15 kilogram of air initially at 2 megapascal. So it's a piston cylinder device. Piston can move. So its initial states, okay, mass of air is 0.15 kilogram. And it's an ideal gas. Initially at 2 megapascal. So P1 2 megapascal and T1 350 degrees C. The air is first expanded isothermally to 500 kilopascal. So the first process is it goes from this state at constant temperature to 500 kilopascal. So P2 is 500. Then polytropically to the initial pressure, and n is 1.2. This is polytropic exponent. So when we have PV to the power n is constant, that is polytropic process. So n is called polytropic exponent or polytropic index. So the next process is PV to the 1.2 is constant, and it goes to initial pressure. So P3 is same as P1. Okay. And finally, there is another step, and finally at constant pressure to the initial state. So it goes back to the initial state, and this process is constant pressure process. So there are 3 processes and it becomes a cycle because it goes back to the initial state. We have to determine the boundary work and net work for the cycle. Boundary work for each process and net work. Okay. Now see, it's an ideal gas and all we have available is, you see what are the tools. You have ideal gas law, PV is MRT. Okay, that is one. Along with this, we have equation for boundary work, integral PdV. In this problem, we don't have to evaluate heat transfer, so we won't have to use first law. Delta U is Q minus W. If problem asked us to evaluate heat transfer, then we'll have to use that also. But boundary work we can get based on the description of the process, integral PdV. And then we have description of the processes, whether it is constant temperature or it is polytropic. So that's all. We are just going to use these equations to get boundary work. Okay, so but before we do that, let us also draw how these processes look like on a PV diagram. Let us say state 1 is here. The first process is constant temperature process, and constant temperature process for an ideal gas is PV is constant. So that is an hyperbola on PV plot, so it will look like this. So this is 1 to 2. Second process is polytropic. and it is actually, it goes back to the initial pressure. So state 3 will be along this line, because P3 is same as P1. So it is, that means it is compressed. And polytropic process is like this, because n is 1.2, it is greater than 1, it will be steeper than isothermal process. Okay, so this polytropic process is steeper than isothermal process. And then 3 to 1 at constant pressure, it goes like this. Okay, so that is the cycle. And we know that work from 1 to 2 will be positive because volume increases. From 2 to 3 is negative, and 3 to 1 is negative because volume decreases. So net work is going to be negative. Okay, because area under 1 2, that is work from 1 to 2, and area under 2 3 and 3 1, that is work from 2 to 1. So the net work will be negative for this. Okay, let us now see. We need to evaluate work for process from 1 to 2, boundary work 1 to 2, and it's an isothermal process. So just like what we did in the last problem, work is PV log V2 over V1. Okay, or alternatively, you can write this as PV log P1 over P2. Okay, this is boundary work from 1 to 2. Let us see what we have and what we'll need to evaluate. Actually, P1 and P2 are given 2 megapascal and 500 kilopascal. We have to use same unit. So these are given. We can evaluate this at state 1, let us say. Correct. There are different ways to do it. One option is I can write this as MR. Okay, PV as MRT, T1 log P1 over P2. Okay, this will give me the answer directly. I just use ideal gas law. So plug numbers. Mass is 0.15 kilogram. Gas constant for air will be 8.314 over 0.02897 times temperature. It is 350 degrees C, so you add 273 to that, times log P1 over P2. Log P1 is 2 megapascal, that is 2000 kilopascal. I converted it to kilopascal, over 500 kilopascal. Okay, so you get this as boundary work from 1 to 2. Okay. Then work from 2 to 3. 2 to 3 is polytropic. And for polytropic process, boundary work is, it will be P3 V3. Let me see. I don't want to use the wrong formula. Minus P2 V2 over 1 minus N. Okay. Yeah. Okay, don't say P2 V2 minus P1 V1, because the process is from 2 to 3. So it will be P3 V3 minus P2 V2 over 1 minus N. And let us see, to do this, we already have P2 and P3 available. So, but we don't have V2 and V3. So I'm thinking what will be the easier way to do this problem. One option is I can write this PV as MRT. So it will become MR T3 minus T2 over 1 minus N. Okay. We already have T2 because T2 is same as T1. And I can evaluate T3. How to evaluate T3? You see, the process from 2 to 3 is polytropic. Okay. So what you have is P2 V2N is P3V3N. That is the process. And it is also an ideal gas. For an ideal gas and polytropic process, I told you there are equivalent equations in terms of pressure and temperature and volume. So we can use the equation which is in terms of pressure and temperature. That equation is P2 1 minus N T2N equals P3 1 minus N T3N. Okay, we can use this equation. Now N is given and P2 and P3, those are available from the data that is given. And T2 is also available. Okay, so this gives us T3. Okay, this gives us T3, and then we plug number here. We already have gas constant for air, mass is given, N is given, and T3 and T2, that will give us boundary work. So the answer you get for boundary work from 2 to 3 is negative 34.86 kilojoule. That is not the only way to do this problem. You could have done it in a different way, but I'm just saying what will be the easiest way. Okay. And then you need work from 3 to 1. So the work from 3 to 1. 3 to 1, the process is constant pressure process. So when you integrate PdV from 3 to 1, because pressure is constant, you can indicate as P1 or P3. It just becomes P times V1 minus V3. Okay. And you can write this as PV is MRT. So it is P1 V1 and P1 and P3 are same. So this becomes equal to MR, okay, T1 minus T3. Okay, we have these numbers already. We have MR, T1 is given, and T3 we already evaluated. So plug those numbers, and that gives us, this work is negative 6.97 kilojoule. Okay, and if you want to find out the net work, okay, you just add sum of all the works, and this is negative 4.65 kilojoule. Okay, so that is for an isothermal process for an ideal gas, or for a polytropic process for an ideal gas, how we do the boundary work thing. This was number 29. Okay, let us look at number 30, and this is very straightforward problem. It says 1 kilogram of oxygen is heated from 25 to 300 degrees C. Determine heat transfer required for a constant volume and an isobaric process. Okay, isobaric means it's a constant pressure process. Let me first clarify that. Isobaric means it is constant pressure. Okay, you see in the name it has bar, and bar is unit of pressure. So isobar means constant pressure. And similarly for constant volume, many times we call them isometric or isochoric. These are constant volume processes. Okay, isometric or isochoric. Now in this problem number 30, we have 1 kilogram oxygen, and it is heated from 25 to 300 degrees C. Okay. Now if the process is constant volume, the first case is constant volume. You apply first law, delta U is Q minus W, and there is no work involved now because boundary does not move, it is constant volume. So Q is just delta U. Q is delta U, which will be, it's an ideal gas. You can write as mCV delta T. Okay, delta U will be mCV delta T. So this delta T is given 300 minus 25, m is 1 kilogram, and CV we can read from the table at average temperature, at average of 325. Okay, so at average temperature you read CV. Let me write down that number. So that is CV at average temperature. Average temperature is around 162 degrees C in this case. So around that temperature you get CV is 0.95, no, 0.692 from the table. Okay, kilojoule per kilogram Kelvin. Okay, so just plug this number here and you get this heat transfer is 190.3 kilojoule. Okay, other situation is if it is constant pressure. If it is constant pressure, then again first law, delta U is Q minus W. In this case there will be boundary work. Okay, because constant pressure, think of it in a piston cylinder device and boundary will move. But because it is constant pressure, you can combine boundary work with delta U, it becomes delta H. So Q will be delta H. And that will be mCp delta T. Okay, delta H will be mCp delta T. So you just plug numbers here. M is given, delta T is given, Cp we can read from table at the average temperature. We read Cv, we can read Cp also. That value is 0.952. Okay. So that gives us heat transfer. Okay, so this was just simple. You are just applying first law and see the boundary work gets combined with delta U if it is a constant pressure process. Okay, let us look at 31. It says argon is compressed polytropically. Okay, polytropically. So the process is PV to the 1.2 is constant because N is given as 1.2. From 120 kilopascal 30 degrees C to 1200 kilopascal in a piston cylinder device. Determine work and heat transfer in kilojoule per kilogram. Okay, so it does not give us the mass of argon. We have to determine answer in kilojoule per kilogram. That means it is asking for lowercase w and lowercase q. Okay. Okay, now work transfer, polytropic process, and it is an ideal gas. So the formula is P2V2 minus P1V1 over 1 minus n. And see, you have to be consistent because I used lowercase w here, which is work per unit mass. This is lowercase v, okay, volume per unit mass. So I have divided the polytropic work equation with m. So you get this becomes specific volume and this becomes lowercase w. Okay. N is given and we have T1. The easiest way to do this will be we use ideal gas law. P2V2 is mRT2, but not M here. This is specific volume, so this will be RT2. So RT2 and P1V1 is RT1 over 1 minus N. Okay. T1 is given. We need to determine T2 and it's a polytropic process. Okay. So it's an ideal gas. So see, this equation is identical to P 1 minus N, Tn is constant. Okay, because it is polytropic and ideal gas, we can use this one. So what you have is P1 1 minus N, P1 is 120 kilopascal, 1 minus N, N is 1.2, so it will be 1 minus 1.2 times T1N, T1 is 30 degrees C, that becomes 303 Kelvin to the power N, equals P2 1 minus N, 1200 to the power 1 minus N times T2 to the power N, sorry, N is 1.2. Okay, you can rearrange this. Actually, before using this equation, you can write it in a different way. Like you can write T2 equals T1 times P2 over P1 to the power N minus 1 over N. Okay, that is just manipulation of this equation. T2 will be T1, yeah, and then plug numbers, that gives you T2. Let me see if I have this number. You get 444.7 Kelvin. Okay, we got temperature. Now we can plug numbers in this equation. So work will be R. Now R for argon will be universal gas constant 8.314 over molecular weight of argon. Argon is around 40. Okay, you can remember some of these if you can. Argon is around 40. To be precise, it is 39.95. Okay, so universal gas constant over molecular weight. But this is gram per mole. So to convert this to kilogram, times 10 to negative 3. This is gas constant for argon. Okay, times T2 minus T1. Minus T1 is 303 Kelvin over 1 minus N. So that gives us work. You get 147,500, and answer will be joule per kilogram. It was lowercase w, so it will be per kilogram, and we did not use any kilo here, so answer is in joule. Okay, or you can say negative 147.5 kilojoule per kilogram. That is work. Okay, now we have to determine heat transfer also in this. For that we apply first law, which is delta U is Q minus W. Okay. So Q is delta U plus W. W we already have, and delta U, it's an ideal gas. You can write as CV delta T. Delta U will be CV delta T. Okay. Now see, it's argon, and you should immediately understand it's a monoatomic gas. For a monoatomic gas, CV is 3/2 R. Okay, CP is 5/2 R, CV is 3/2 R. So it will be 3/2 R delta T plus W. So just plug numbers here. We have temperatures, we have gas constant I gave you, and we have this work already. Put numbers in this equation, you get 103,300 joule per kilogram. So that gives you heat transfer. Okay, so we are getting boundary work by the formula for the boundary work, which is integral PdV, and heat transfer by using the first law. Okay. So let us look at number 32. I'm going to do 3 more problems and then we will be done with this topic. It says 15 kilogram of air in a piston cylinder device. Okay, 15 kilogram and it's air. It is heated from 25 to 77 degrees C. It was 25 to 77 degrees C by passing current through a resistance. Heat loss is 60 kilojoule. During the process, there is also heat loss. So I'm showing that in this direction. Okay. And pressure remains constant. Determine the electric energy supplied in kilowatt hour. We have to determine the energy supplied from this. Okay. Okay, so this is the system. In the problems I was doing, actually I did not draw the system. Ideally that should be done, but because it was sort of very clear what we were talking about, I did not even draw it. So the first law is delta U equals Q minus W. And you see what types of work we have in this problem. We have boundary work, because it's constant pressure process, boundary moves, and there is also electrical work. Okay, electrical work. This boundary work term I can combine with delta U, that will become delta H. And so by rearranging this, you get this electric work will be Q minus delta H. Let me see, it is right. Electric work becomes positive Q minus delta H. Okay, that's what it gives. Okay. You can write this as Q minus, okay, M delta H. Okay. And for delta H, see, we have two options. It's an ideal gas. Okay, one option is take this as Cp delta T. So we can read the value of Cp at an average temperature. So this is 25, this is 77, at some average temperature. We can read the value of Cp, it will be Cp delta T. Or other option is from the table. We can read the value of enthalpy. We can read enthalpy at 77 degrees C and at 25 degrees C, and just take a difference of those enthalpy values. Actually, it does not matter which one you use, you are going to get an answer which is very close. Both will give you very similar answer. Okay, so let me stick to, I'm just going to take a value of Cp and substitute that here. So electric work will be Q minus M delta H is Cp delta T. And Q, heat transfer is 60 kilojoule. Okay, but it is negative because this is heat loss from the system. So it will be negative 60. Negative 60. And see, I took this in kilojoule. Okay, so we have to see that. Either convert this to joule, then everything is in joule. Or if I'm taking in kilojoule, this Cp also I will take in kilojoule. Minus M, that's 15 kg. And Cp of air, if we read from table, it is 1.0065 in kilojoule per kilogram Kelvin. So I'm being consistent here. Okay. Times change in temperature, that is 77 minus 25. So this gives us electric work. You get actually negative 845 kilojoule. Okay. but we have to answer in kilowatt hour. So if I divide this with 3600 second and multiply with 1 hour, okay, that is same, 1 hour is 3600 second, and this kilojoule per second, that becomes kilowatt. So now your answer will be kilowatt hour. So this gives negative 0.235 kilowatt hour. Okay. And this is negative because work is done on the system. Okay. So if we have to say how much energy is required, it will be 0.235 kilowatt hour. Okay. You just take off negative sign. Okay. Let us look at number 33. It says a piston cylinder device contains 0.8 kilogram of nitrogen at 100 kilopascal and 27 degrees C. So that is initial state, state 1. And it is compressed polytropically. So the process is PV, N is 1.3. This is constant, that is the process. Until volume becomes 1/2. So its final volume is half initial volume. We have to determine W and Q. So again, an ideal gas polytropic process. So you see the boundary work integral PdV, and this will be for a polytropic process P2V2 minus P1V1 over 1 minus N. Okay. And I can write this as, we have to see what will be the easiest way to solve this problem. We have pressure, but see volume is not given. We'll have to evaluate V1 and then also P2. So instead of this, if I take this as MR T2 minus T1, because it is ideal gas, so PV is MRT over 1 minus N. Okay. Then T1 is given, N is given, M is given, and T2 I can determine in one step. So this is easier. Okay, if I, instead of using this, if I use this formula, it is easier. Now, if you remember, this PVN is constant, and if it is an ideal gas, this is same as TVN minus 1 is a constant. Okay, by using ideal gas law, we can change this into this, and it's very easy. Actually, you don't have to remember this one. You can work it out very easily based on this. Let me show you. Because ideal gas law is PV is RT. Okay, or so this volume, or sorry, this pressure is proportional to temperature over volume. So all you have to do is, instead of this pressure, substitute temperature over volume. So then it becomes T V to the N minus 1. It will be some other constant. Okay, but TV N minus 1 is constant. In this case, we can use this formula because we are given the volume ratios. It will be easier. So based on this, you get T2 is T1 V1 over V2 N minus 1. Okay. And just plug numbers. T1 is 27 degrees C. Convert that to Kelvin. It will be 300 Kelvin. V1 over V2. V1 is twice V1. So it will be just 2. Okay, so see, what we need is just the ratio of volume. We did not have to determine the actual volume. We just need this ratio, which was 2 to N minus 1, 1.3 minus 1. So that gives us T2. You get 369.3 Kelvin. and then plug numbers here. I'll do that quickly. The boundary work is M is 0.8 kilogram. Then gas constant for nitrogen will be 8.314 over 0.028. T2 minus T1 over 1 minus N. Okay, so this gives you boundary work 54800 joule. And we have to determine heat transfer also. For that we apply first law. So delta U is Q minus W. Okay, now don't combine work with delta U, because this is not a constant pressure process. You can combine boundary work with delta U only for a constant pressure process. This is not constant pressure. So Q is delta U plus W, and delta U is mCv delta T. It's an ideal gas. Okay, plus 1. And then just plug numbers here. M is 0.8 kilogram. Okay, Cv for nitrogen. We can read from table that value is 0.744. This is kilojoule per kilogram Kelvin. So I'm converting this to joule. Times delta T, we have that number, and W also is in joule, we have that. So just do the calculation. It gives 13600 joule. Okay. Okay, now this is the last problem I am going to do. Number 34. And it says 10 gram of nitrogen is in a spring loaded piston cylinder device. Okay, so this situation is like this. It's a piston cylinder device, and there is a spring here. Okay. And you have 10 gram of nitrogen. Spring constant is 1 kilonewton per meter. So we indicate that as K is 1 kilonewton per meter. And the piston diameter is 10 centimeter. When spring exerts no force on the piston, okay, so the spring is not compressed or extended, nitrogen is at 120 kilopascal and 27 degrees C. So you say that is the initial state. It is heated until volume increases 10%. So after heating, stage 2 is its volume is 1.1 V1. It increases by 10%. Determine change in specific internal energy and enthalpy of nitrogen. Okay, so we have to determine change in delta U. This is specific internal energy change, and delta H. Okay. So first see how this process will look like on a PV diagram. Now, because this is a linear spring, let us say its initial state is here. Okay. As this piston moves up, volume increases. Actually, the pressure will vary linearly. Okay. And the reason is, if it is a quasi-equilibrium process and if it is linear spring, then the force this spring is going to exert on the piston is linear with respect to the displacement of this piston. So it will be a linear thing. So as volume increases, pressure will increase linearly. So it will be something like this. Okay. So although the problem does not say, but if we have to determine how much is the work done by the gas, it will be this area. Okay. And because this is a trapezium, we can determine the area. It will be half P1 plus P2 times V2 minus V1. Okay, so we can also determine the work involved, knowing that it is a linear relation between pressure and volume. Okay. But right here, to determine delta U and delta H, let us see. Delta U is CV delta T. And T1 is given, that is 27 degrees C. So we just have to determine T2 final temperature. That will give us delta U. And similarly delta H. Delta H is Cp delta T. Okay, so we need to determine T2 and then plug numbers that will give us the answers. So how to get T2? What we know is its volume becomes 1.1 V1, and there is this spring also, its spring constant. We have that information also. Let us see. Okay. Actually, we can find the compression of the spring and use that information to get final pressure. You see, let me write here. This final pressure P2 will be the initial pressure P1 plus the pressure that is exerted because of compression of this spring. Okay, because of compression of this spring. Okay. If let us say compression of this spring is X, then the force because of that on the piston will be Kx. So this is force, and force per unit area, that will be like a pressure because of that spring, will be this per unit area. So pi by 4 d square. Okay, so this will be the final pressure. Okay, let us write this X also in some other form. We have K, D and P1, but we don't have X. So let us manipulate this. You can write this as P1 plus this X. This will be the change in volume, V2 minus V1 over the piston surface area, pi by 4 d square. So this thing is X. Because change in volume over piston surface area, that is the distance the piston traveled, that is X, that is the compression of the spring. So this times K, and then we have pi by 4 d square, another term here. So it will become square of this. Okay. Okay. Now see, P1 is given, K is given, diameter is given. V2 minus V1 is 0.1 V1 because V2 is 1.1 V1. So V2 minus V1 is 0.1 V1. We need V1. And V1 we can get based on ideal gas law. V1 will be mRT1 over P1. And all these numbers are given. Okay, so we just have to substitute numbers here. I'm not going to solve it, but if you like, you can verify. Let me just give you the numbers you get. You get V1 is 2 cubic meter. You calculate pressure, it turns out to be 132,000 Pascal. Can be consistent with units. So if this pressure is in Pascal, volume in cubic meter, diameter in meter, then this spring constant has to be Newton per meter. Okay, don't use any kilo here. This will be Newton per meter. Then you get this pressure in Pascal. Okay, and once we have P2, we can get T2 based on P1 V1 over T1 equals P2 V2 over T2. Okay, we can use this. We have T1, V2 and V1. V2 is 1.1 V1, so we know their ratio. And we have P1 and P2, so this will give us T2. And then plug numbers. So you get delta U is CV delta T. CV from the table is 0.743 kilojoule per kilogram Kelvin times 363 minus 300, and you get 46.8 kilojoule per kilogram. And delta H kilojoule per kilogram. Okay, so this is the last example I wanted to do, and I will stop at this point. But again, the main thing is, so in general, like you read, if the substance is water or if it is a refrigerant, you have to read properties from the table, from the subcooled liquid table or superheated vapor table. But there are special cases. One of those special cases is if the substance is incompressible. And for incompressible substance, we get all these some simplifications we talked about, that there is only one specific heat, and delta U is C delta T, and similarly we have delta H also. So we can use that if we are dealing with liquids or with solids. Okay, so there is a simplification. And similarly, all gases behave as ideal gases under certain situations, which are low reduced pressure or high reduced temperature. Low PR and high TR, then they behave as ideal gases. So we get PV equals RT. And there are different forms of this law. You can write in terms of universal gas constant or gas constant, specific volume or total volume. So you have to be consistent. And based on this law, you get internal energy, enthalpy, CP, CV, all these things are function of temperature only. And you also get CP minus CV is R. And you get dH is CPdT and du is CVdT. So I showed you how you use these things and apply also first law. So actually the rest of the thermodynamics in terms of application of first law is going to be very, very simple if you have understood what we have discussed so far. Because in all the problems, whether it is a cycle or later on we are going to talk about the flow situation also, when you have an open system, not a closed system, you have to deal with all these properties. It might be an ideal gas or incompressible substance or other pure substance. So if you have understood what we have discussed so far, then in the rest of this course the application of the first law is going to be very, very easy. Okay, so I'll stop at this point. Thank you.